Good afternoon, everybody, and thanks for joining NC Transportation Center of Excellence on Connected Autonomous Vehicle seminars. The past seminars are already available and posted on the website. If you have missed any of those exciting talks, feel free to go and check those talks. We would like to take this opportunity to thank NC-DOT for enabling this research, as well as the sponsors of the project, other sponsors, including Downtown Greensboro, Verizon, and RTI. And today, we are delighted to have Dr. Amirhossein Ghasemi as a speaker. His talk is very interesting, is on the topic of toward seamless human action handover, an adaptive haptic shared, what happened? Sorry. An adaptive haptic shared seating control for ground vehicles. Dr. Ghasemi received his bachelor degree in mechanical engineering from the Ferdowsi University of Mashhad in 2005. His master degree in mechanical engineering from NC-CAV University in 2008, the university that I did my undergrad, and he received his PhD degree in mechanical engineering from University of Kentucky in 2012. He's currently an assistant professor in Department of Mechanical Engineering Department at University of North Carolina at Charlotte. His research focus on modeling and control of shared paradigms in which a group of human and intelligent robots are interacting with each other, and of course the applications to the autonomous driving is one of the things that we're going to be having today's talk about. With that, I would like to again thank Dr. Ghasemi, and the stage is yours.
Thank you very much. Thank you for inviting me. I am really happy to be here and sharing my research project and research results with you all. Let me share my screen and ask if you can see my screen. Okay. Well, again, thank you very much. Do you see my screen? I cannot see all, so if you can just say.
We do, but it seems that it is partitioned into three parts. I don't know.
No, we are seeing it. This is good.
Yeah.
Okay.
It's good. Okay, it is good on your side. Okay. Then that's the problem on my screen. Go ahead.
Perfect. Today's talk is on the topic of seamless human automation handovers. Specifically, I am talking about our research on designing and developing adaptive haptic shared steering control and path planning paradigm for ground vehicles. My name is Amirhossein Ghasemi, and I am an assistant professor at the Department of Mechanical Engineering at the UNC Charlotte. Before I discuss the project, I'd like to use this opportunity to introduce my lab to you all. My lab is the Human Automation Interaction and Control Lab. What we do in the lab, we are basically, our research is focused on developing some control algorithms for partially to fully automated systems. We also design and develop interfaces to enhance the interaction between human and machine. And then we study the human users in shared control paradigms. Two projects that currently I am working on are focused on human-machine interaction inside the vehicle and outside of the vehicle. With the outside of the vehicle, basically I am focusing on developing some control and traffic management strategies for a heterogeneous traffic control network, where we have some autonomous vehicles and human-driven vehicles interacting with each other. And then inside the vehicle, I am also looking at human-machine or human automation collaboration for steering the vehicle. To just discuss a little bit about my the heterogeneous traffic control project. Basically, in this project, we are interested to understand to what extent the performance of such a nonlinear, uncertain, partially controllable system can be improved. Here in this project, we are considering the autonomous vehicles as a controllable agent, that they can receive some information from the infrastructure, and then based on the information that they receive from the infrastructure, they can adapt their behaviors. However, the human-driven vehicles here, they are some non-connected, uncontrollable agents, and we are interested to understand for this, again, uncertain, nonlinear, partially controllable system, to what extent the performance of the whole system can be improved. So what we are doing here, we are developing some learning-based predictive control algorithms at both macroscopic and microscopic level, where we are dealing with the uncertainty as a state and input-dependent uncertainty, dealing with the uncertainty as a state and input-dependent, and learning that uncertainty in real time, and applying that uncertainty in real time will allow us to design some more aggressive controller, aggressive, I mean, in comparison with our robust controllers, so that we can push the performance a little bit more. And then we also develop some distributed optimization algorithms to be able to implement these control inputs in real time. So, but today's talk is about a project that I started working on when I was a postdoc at University of Michigan, and it was about human automation collaboration for steering control of a semi-autonomous vehicle. This project originally funded by Haptic, and then I am still working on this project, and we may get some funding from Army on that as well. It is still not clear, but we are hoping for that as well. So the motivation behind this project is that, as you all know, human automation teaming getting more and more interest because of the great promise that the autonomous vehicle has. With regard to the military applications, autonomous vehicles can increase the personal safety, they can increase the mission performance. And with regarding to the commercial applications, autonomous vehicles, we are hoping that they can increase the road safety and the mobility and life quality for us. For that reason, there are many frameworks that have been defined where they are studying the levels of autonomy. One of this framework is ALFUS, which is Autonomy Levels for Unmanned System. In ALFUS, we are looking at the autonomy level with regard to human independence, how much your autonomy or algorithm is independent of a human user, and then how much it can address the issues and challenges regarding the mission complexity and environmental complexity. And some of the examples for mission complexity is the time constraint that you may have for your mission, the precision constraint that you may have, the level of collaborations, resource management, there are risks that you may have, and these are some complexities that can be defined as a mission complexities with the environmental complexity, noise, the dynamic nature that your vehicle can perform in, maybe the obstacles, the size of the obstacles, whether the obstacles are moving or dynamic obstacles or not, the terrain itself, the light, they are all can pose some challenges in the design of your autonomous vehicle or your autonomy algorithm. And then with regard to the human independence, we want our algorithm to be capable of accurate sensing, have a good perception, analysis, communication, and decision-making capabilities. So the goal for us as a control and autonomy engineers is to be able to design an algorithm that is independent of human user and can address as much as mission complexity and environmental complexity as possible. However, what we have here so far, our full automation systems, they only can address a very small fraction of the problems regarding the mission complexity and environmental complexity. While we can work on improving our algorithms, it is important for us to also consider another possible solution. And the possible solution is use the human user as a resource, as an off-board resource, to resolve some challenges that may arise when the autonomy is working in the new environment. And that's when the research question becomes to mind, and how we should merge the best of the two agents, how we should use the human capabilities such as perception, the judgment, the experience that the human may have with dealing in the new environment, with the best of what automation can perform for us, the precision that the automation can provide. Here, I need to emphasize that adding human and automations, it may not necessarily always be basically leads to a better performance. Because human and automation, they may see the world differently, and therefore it is possible that they may get to some conflicted scenarios. And because of these conflicted scenarios, we need to understand how we should resolve these conflicts between human and automation. And that's when it is important to understand how the control should be transitioned between human and automations, or how should the control be combined between human and automation. For that reason, they have been developed different shared control paradigms, and these shared control paradigms are mainly different on the mechanism that they use for transferring the control between human and automation system. The simplest paradigm is the supervisory control, when the automation has the full control on the vehicle, and the human is basically supervising the actions of autonomy. Here, we really do not consider that as a shared control paradigm, because human and automations are not in the same level. They are not really doing the same task, but human just like supervising the control. One of the shared control paradigms is switch-based paradigm. In the switch-based paradigm, we can have two options. In the first option that's shown here, which we call it active safety. In the active safety is the paradigm where the human has the has the control of the vehicle or the task. Here with the vehicle and the task, we are always considering the steering the vehicle. So human normally has the control of the vehicle, but in the dangerous situation, the controller will come and take the control from the human. And an example of it, you can see like at the ABS brake system. And then another paradigm here, we call it autopilot, where basically the automation has the primary is responsible for performing the task. However, in the dangerous situation, human can jump into the loop and take the control from the automation, and that's what happens with the cruise control. The problem with this switch-based control paradigms is it has been shown that these switch-based paradigms, the transfer time between human and automation is a little bit long. And then also, if one agent is not in the loop, it will be hard for the agent that is out of the loop to understand the other agent has some problems and faults, and then jump in and take the control from the faulty agent. So there are some misuse in using this switch-based control, and that's why recently people are thinking about combining human and automation's control commands continuously. One of the approaches or one of the paradigms that people use to combine the human and automation control command is through a paradigm called input mixing shared control paradigm. In the input mixing shared control paradigm, the control command and the automation commands will mix through some weighted function, and that weighted function can be an adaptive function that goes between human and automation. And the problem here is defining this alpha normally is defined by some third order algorithm. Again, you can imagine that what if that algorithm is not programmed sufficiently for these new complex areas that we have. Or another problem that we can see that the human, since the human is not directly connected from the automation, human needs some additional process to understand or basically understand automation desire from the feedback that it gave from the system. So I'm processing that. So it may be a little bit time consuming for the human to understand what exactly automation wants to do. That's why my research has been focused on haptic shared control paradigm. In the haptic shared control paradigm, both human and automations, they both apply their commands on the steering wheel. And the steering wheel as a haptic interface here allows the human and automations to be, their dynamics to be coupled. And basically this coupling will allow us to not only apply our control commands, but also be able to sense what the other agent wants to do by basically through the haptic feedback that we can get from the steering wheel. Any questions?
Yes, may I have one question?
Sure.
So basically with this mechanism, what you are doing in the previous slide, the blending mechanism that you had, alpha was typically a constant value. Now you make alpha as a sort of function of the haptic feedback. Is it what you're doing?
The difference is no. The difference is in the previous in the input mixing approach, the alpha can be adaptive, can be variable in time, but the alpha is happening in the vehicle. The alpha is happening in the there is a board, and basically what is happening is human does have its own steering wheel, automation has its own, let's say, steering wheel, and the steering command of the human and the steering command of the automation, they are all going to the vehicle, and it will get combined through some mechanism, and then human gets this feedback back. So basically, each of the agents, they have their own steering wheel. So there is no coupling between these two agents at the actuator level. You know, the coupling comes from happens in the system level.
Thank you.
Yeah. But here again, that is a really good question. Thank you very much. But yes, here the coupling and the sensing happens at the actuator level, and that's the main difference between haptic shared control paradigm and input mixing control paradigm. In the input mixing control, so because both of them, so in the haptic shared control paradigms, human applies this torque through a limited impedance through his body, and his body does have some limited impedance. By impedance, I mean like a limited stiffness and damping of. You can assume that your muscles are, they have limited stiffness and damping. On the road, we may have some torque, apply some disturbances on the steering, and the automation needs to be designed to have a limited to have a limited impedance as well, and this limited impedance should be in the order of humans' impedance. And then, in order that if human disagrees with what automation wants to do, human can basically tightening up his muscles and apply a higher torque, and then basically override what automation wants to do. And then whenever human is agreeing to what automation is trying to do, he can just relax and let the automation do whatever the automation needs to do. So we are looking at automation here as instead of having an infinite impedance or like a motion source, we are looking at it as a source with a limited impedance. So so here the first question that we wanted to ask ourselves is basically when there is a complexity in the system, and when there is a need for transition of a control between human and automation, and that transition again may happen because human and automation, both of them are subjected to errors. Which of these shared control paradigms are the best paradigm for us? So we did. So basically, our objective, the first objective for us, was quantifying the benefits of a haptic shared control in comparison with the alternative shared control paradigms. Again, this is happening, this transition of control is important for us because, again, we are interested in scenarios that there is a need for transition. And if you assume that your human agent is 90% reliable, your automation is 90% reliable, for let's say that you consider the task to be obstacle avoidance, maybe in 81% of the time, both human and automation sees the obstacles and they can avoid it. But there are 18%, 9%, and the 9% that one of the agent is not capable of seeing or has some fault. So by designing and then obviously there is a 1% that the accident may happen, and that's why we need to design a more, the material of the vehicle should be researched on. But what we are doing, we are saying that, hey, if we design a very good shared control paradigm, a very intuitive shared control paradigm, we should be able to improve the performance of the system up to 99%, from 81% to up to 99%, if our shared control paradigm works perfectly. For that reason, we did some case study, where in this case study we used a fixed space driving simulator. This fixed space driving simulator, we have a motor, we have a motorized steering wheel where the automation's commands come through the motor and can control the steering wheel. The steering wheel has an encoder that, and then it has some torque sensors. The torque sensor is a differential torque sensor that can determines basically the difference between the torque that applies by the motor and the torque that applies by the automation. sorry, by the automation and by the human, and then basically it can tell you a little bit about if they are in the agreement or disagreement. Obviously, if this differential torque is high, it means that the two agents are going in like they have some disagreement between each other. So the task for us in this case study, we asked our participants to drive a vehicle, and we asked them to track the center line, but also avoid the obstacles. The path is shown here, and this simulated model happens to be on the Simulink virtual reality toolbox. So we considered 5 case studies where basically 3 of them are shared control paradigms. One is active safety, one is haptic shared control, one is autopilot. Again, in the active safety, the human has the control originally, and then the automation takes the control in dangerous situation. In the autopilot, the automation has the control primarily, and then in the dangerous situation, human takes the control. And then haptic, there's a continuous interaction between human and automations. We considered a fully manual case where the human has the whole control of the vehicle, and then we also considered the full automation case. So we tested with 10 drivers, and each driver tested basically did 3 repetitions per case per the driver. And then we had these participants were trained initially, and then we randomized these 3 cases as well. So next, I want to show you this example of an autopilot case. Again, here the automation is in control of the steering wheel. It is controlling the steering wheel. But when a human wants to take the control back, the human can basically put his hands on the steering wheel and apply a quick jerk. This is like something similar mechanism that Tesla is doing it, and then it can re-engage the automation by clicking the button. So that's the example of an automation autopilot. Again, I let you to see it one more time. So automation is on, automation is controlling the vehicle, and then whenever a human wants to take the control, it applies a quick jerk, and the automation goes off, and the human click, and then the automation back on, and then you try to come into the center line and avoid the obstacles. This is the example of haptic shared control. It is very hard to see that in the haptic shared control, obviously there is a motor that applies its torque on the steering wheel, but human's hand is also on the steering wheel. And then whenever human wants to take the control, it can just like tighten up his muscles and then take the control from the automation system. The automation is always running under the background, so there is no engagement and disengagement here. So we considered, because we wanted to model the fault in human and automation, we considered that there are 10 obstacles on the path, which 6 of them are visible to both human and automation, and only two of them is only visible to the automation, so automation can see 2 of them when the human cannot see, and then the other 2 is when a human can see, but the automation is not cannot see that obstacle. Basically, we are not passing the information about that obstacle to the automation system. So we were looking at the obstacle heads and the tracking error. We basically divided the path into 2 main sections. The sections in white, where we calculate our tracking error, and then the zone or the part in gray, which is around the obstacles, where we just look at the obstacle heads. So comparing the results, we compared again the hit percentage, the number of the obstacles that was hidden, and the error. Obviously, for the fully manual or the teleoperation and fully automations, because we engineered them that 2 out of the 10 obstacles were invisible to them, we have a 20% hit as well. However, when we have a shared control paradigms, we saw that in the haptic shared control, the number of obstacle hits is significantly smaller than the others, especially with active safety. Here, this star indicates the statistically significant difference based on an ANOVA analysis. And then for the error, we also saw that obviously fully automation has the lowest error, but comparing these three shared control paradigms, we saw that the haptic shared control has a smaller error regarding to the active safety and autopilot. So it shows us that adding automation through haptic displays can improve the lane keeping and the obstacle avoidance. But we were interested to see more carefully how human and automation interacting in these shared control paradigms. And I want you to look at these results. These results shows basically we add the path of all the participants that are going through an obstacle that is visible to both human and automation in the active safety. So basically we added all the path of all the participants here for each case here for the active case, active safety, haptic shared control, and autopilot. Sorry, do you have any questions? No? Okay. And then for the cases when there is a no fault, when there is a human fault, human cannot see it, and then when there is an automation fault. So one specific case that I want you pay attention is in the autopilot. Autopilot is the case when the automation is in control and then a human takes the control from the automation if the human realizes that the automation does not perform correctly. There is a low approaching distance for this case. It means that the human was not really prepared to take the control. It realized that it realized a little bit late for human realized a little bit late that, oh, okay, this automation has some fault. I need to take the control for it. And that shows this low approaching distance, and then this high confidence area here. When we're looking at the haptic shared control and you're looking at it more closely, we see the same thing that is happening for us as well. Again, when we have a fault in the automation system, in the haptic shared control paradigms, we see there is this approaching distance is a little bit smaller in this scenario. One of the hypotheses that we had here is we assumed it is because we set the gains of the automation controller or the impedance gains of the automation controller to be constant, to be non-invariant. And maybe we have set them high or low, high a little bit, and that was a little bit hard for the human to take over the control from the automation system. For that reason, and we also realized that looking at the case where the automation and human both sees the obstacle, but they may have different preference on how to avoid the obstacle, might be a dangerous situation. You can imagine that previously we always thought that, okay, if the obstacle is available to both you or is visible to both human and automation, that's like a easy case for us to solve. But when we were doing the simulation, we realized that there are cases that human is decided to go from the left and then automation decides to go to the right. And obviously because of the haptic shared control paradigm structure, those torques cancel out each other, and then the vehicle may hit the obstacle. And that's why we thought that, okay, let's rethink and let's think about designing an adaptive haptic shared control paradigm. So here the research question for us was, within haptic shared control, how we should minimize the trade-off between what human wants and the safety and the performance of the task in the haptic shared control paradigm. And that's why the objective for us was to develop a modulating mechanism for the automation's impedance controller gains to enable the transition of control authority between human and automation and dynamically. So what?
Sorry, may I have one question? So far,
Sure.
before this objective, the human was in control of how much haptic control, haptic feedback is going to be applying. Now you're going to have an external algorithm to make that balance between the human input and the automation input, correct?
Yes. So I am gonna okay. Let me go through this and this is slide, and I'm gonna answer you right now. So in a haptic shared control paradigm that we have a motorized steering wheel with human is controlling the steering wheel and automation is controlling the steering wheel. And normally the automation can control it through some impedance controller. You can assume like a PID controller. So what we did, we are considering the human as a two-level controller, a higher level controller, which in brain you can determine your intent, go left, go right, and then in the lower level, which is the biomechanics of it, you can apply the torque that you are applying on the steering wheel. So by modulating these gains, by modulating the stiffness and the damping in the muscles, you can take the control from the automation or get it or yield it to the automation. Previously, in the haptic shared control paradigm, we were setting these parameters of my automation system, my PID controller. Those gains were constant. They were not changing. So if human wants it to take the control, it should increase its gains to be more than ZA, ZH to be more than ZA. And then if it wants to yield the control back to automation, it should relax so ZH becomes smaller than ZA. Okay, so this ZA was fixed. Again, automation, we are assuming the automation has the same structure of the human. It has some algorithm that determines the automation's path, and then that automation path will go through, again, some lower level controller, like an impedance controller that applies the torque on the steering wheel. So although human can modulate its impedances as they wish, we assume a very simple model on how they are modulating their impedances through a first order equation, maybe with some disturbances, but this gamma H is their modulation policy. And then we assumed that, okay, let's make the automation has some variable ZA as well. And let's now determine this modulation policy, if we are showing it with gamma A, such that we can find the optimal or a trade-off between human's preference and the safety and the performance of the task. Again, human is a very complicated model, but for this study, we assumed that human is we can model it as simply as a mass spring damper system that is connected to a motion source that is connected to its theta edge. And then we also have the same structure for our controller. Our controller is a very simple impedance controller. So this is a little bit complicated block diagram, but I wanted to walk you through it. In the lower part, here is the Laplace block diagram of the haptic interface. It is basically the dynamics of the human and automations and how they are basically interacting through on the steering wheel together. Here we assumed that we are measuring the steering column angle, and then we're also measuring the torque sensor. The human can modulate its impedance with some function, gamma H. And the goal for us is to determine gamma A such that a cost function is minimized or optimized. So to minimize or maximize this cost function, we need some information that from a high level controller. That is, this high level, these blocks, each of them are the subject of our current studies, some of them, and then some of them are the subjects for the future studies. But first of all, we need to know the interaction mode that we are in. We need to know whether we need to take the control from the automation or from the human, whether we need to be acting as an active safety or as an assistive. We need to have some knowledge about the human, and then we need to also have some, which meaning to measure ZH and theta H in real time, and then meaning that have some algorithms to determine the intent or for the automation systems. Having this knowledge available, our goal was to determine gamma A, or the optimal modulation policy. So for us, the cost function that we defined here, it was it has three terms. It has the first term is focused on how far the steering angle is different from a human. And the second is the steering angle, how far is it different from automation? And then the question is, what is the disagreement between the two agents, which is subjected to our dynamics of the human automation interaction on the steering wheel. You can imagine there are two possible interaction modes. When the automation decides that WL1 is bigger than WL2, it means that it is giving more weight to the first term. Is basically in the assistive mode. It is basically try to give the control to the human, and then when it is in the active safety mode, WL2 become WL1. So for now, we consider, again, for now we are considering these weights are constant, but in the future, we are hoping that determine some adaptive law for modular or changing these W's adaptively as continuously the different scenarios can happen. So we used a CGMRS, which is an iterative solver for solving a nonlinear MPC problems. We adopted and solved our nonlinear problem. Here are some of the numerical results that we have, and here the first column is a non-adaptive. By non-adaptive means ZA is constant, and adaptive means ZA is changing with time, changing such that the cost function is maximized. So the first column here is the steering angle theta S and the human's intent theta H and theta A. Obviously theta H and theta A, theta H is the human's intent. There is an obstacle, human wants to go to the right of the obstacle, automation wants to go to the left of the obstacle, and basically if both human and automation, they have the same impedances, they cancel out each other and they hit the obstacle. However, adaptively in an assistive mode, again in the assistive mode, it means that automation wants to yield the control to the human. Automation yield the control to the human, and basically we have this safe maneuver here. The differential torque is much bigger in the non-adaptive case with regard to the adaptive case. In the non-adaptive case, human will feel there is a resistance on the steering wheel, but in the adaptive case it doesn't, and that's because basically automation is adopting a very small impedance. Basically, automation becomes very reduce its role, and that's why this basically a human cannot feel a fight on the steering. For the active safety mode, Basically, again, in the active safety mode, the human is trying to take the control. So, automation tries to take the control, and that's how automation takes the control from the human, with at the expense of increasing the fight. At the expense of increasing the fight, it will take the control from the human by increasing its gain, by increasing its impedance. We tested our algorithm and our solver through a process in the loop to just make sure that we can run it in real time. We look at the horizon view and the iterations that is happening at CGMRS, and we looked at the two cases, basically two modems using Arduino Amiga 25060 and STM Discovery. Basically, using both of these two microcontrollers, most of the time we were able to run this our algorithm in real time. There are two cases that basically the execution time is more than 1 second, which we are assuming that if the execution time is less than 1 second, it is kind of acceptable for us. But in majority of the time, our solver was able to produce an optimal modulation policy in real time. We did some test studies. Again, these studies we just recently started doing it this last month. The problem is almost the same, the experimental almost the same, and we decided to look at the non-adaptive haptic shared control with the adaptive haptic shared control. And again, in the non-adaptive ZAA is constant, but in adaptive ZAA is changing with time. We had one driver which with 1 repetition per non-adaptive case and 2 repetition per adaptive case. And we again considered 6 and 10 obstacles, which 6 of them are visible to both agents. 2 is only visible to automation, and the other 2 is only visible to the human. Here, sorry, I don't know how to get rid of that, but here we used grip force as a proxy for human impedance. Because we do not have a direct measurement of human impedance yet, we use this grip force as a proxy for humans impedance. So basically what we mean is, if human wants to take the control, probably they are holding the steering wheel tighter, and then if they want to yield the control, probably they loosen up and they are holding the steering looser. So there is a grip force here, and then the relationship between grip force and ZA is through this equation, that when GF is very small, it means that when the grip force, like human, is not really like holding the steering wheel, then ZA is high, and then when it is GF is very big, ZA become very, very small. So this is just showing here the red showing the grip force, and the black is showing your ZA, how is it changing. As soon as the subject is holding the steering wheel, ZA and adaptively changing. Yeah. So we did this test again. Besides the other the mobility metrics that we had before, we now looking at the differential torque. So looking at the results, we see that, again, when talking about non-adaptive haptic shared control, we saw that in the non-adaptive haptic shared control, we had this low approaching distance. But this has been removed a little bit in the adaptive haptic shared control paradigm. So I believe, like, and that's what I believe is, as soon as human understand that automation has some fault, it tries to take the control, and it holds the steering wheel very tight, and suddenly the automation, instead of fighting it back, it understands that, okay, human wants to take the control. I need to just like reduce my involvement, and so I am reducing my ZA, and that's why human without any fight can control the steering of the vehicle, rather than here human wants to control, he needs to increase, and there is this bias force over there that human needs to overcome with it. Looking at the differential torque, we saw a significant difference when the obstacles are visible to both human and automation between adaptive haptic case and non-adaptive haptic case. We didn't see that much difference in the other two cases when there is a fault in one of the agents. We need to do more analysis on this matter and increase the number of subjects and more accurately see why there is no the differential torque is not changing that much. But in the adaptive, when there is no fault, obviously adaptive haptic shared control does have a much smaller differential torque, meaning there is a less disagreement between human and automation system. As I said, there are a couple of directions that we are taking right now, or we are working on. One is basically developing a more sophisticated model of a human automation interaction. Basically, you can model the human machine interaction as a the model that we are working on is a function is a x star is equal to f plus g, which f is a nominal model of human machine interaction. Again, same as our mass spring damper, for instance. And then there is uncertainty in the model and in the variables of the human and everything, which can be a state, input, and the parameter dependent. We are applying a couple of estimated UKF, uncentered Kalman filter based approaches to identify our F and identify the parameters of human, or in model of the human. And then we also apply some learning-based approaches, like a basically Bayesian neural network, to characterize the uncertainty on the system. This is one of the projects that we are currently working on. And the other project that we are working on is study the role of convention. Convention means how human and automation basically interacting with each other through repeated interaction. Basically, here you can imagine that we assume this cost function for the automation system, but human can have its own cost function, and human depends on how human selects its weights for its terms. Human can have selfish behavior, it meaning that human wants to take the control all the time, or selfless behavior, or neutral behavior. For whatever behavior the human, and then not only this behavior in the low level, this behavior can be applied in the higher level when the human is deciding about the intents of the human. So go ahead. So now the question is how we should determine like a partner-specific conventions from task-dependent representations, how to characterize the map from the space of conventions to the outcomes of the human-machine collaboration, and then how to influence one agent to reach to a desired equilibrium. Here, because human can select any way, any of these weights and change any of these weights, there are multiple equilibrium, multiple optimal interaction plan, and but maybe which is different from one agent to another agent. And we need to understand, okay, if one agent wants to reach to a specific equilibrium point, how we can reach to that for this agent, and then for the other partner, how we can reach to the other equilibrium point. And then we have we are also hoping to use this experimental platform on a ground vehicle. We have motorized this golf cart. We have a off-board and on-board motorized station, and then we have a LiDAR, GPS, and everything. And I wanna show you this small video from the car that we had at Michigan. It was basically the same idea here. Here, these two steerings are communicating through a radio communication. So here the off-board can control the on-board. So here we are calling the second agent as a wizard, or the automation. It can control the off-board, the vehicle, and then we have this bimanual communication between the two agents. And then when they are interacting, both of them, they feel whatever the other agent wants to do. Finally, I want to thank you all for attending this talk. I want to thank my students, Mr. Vahidi Zadi, Mr. Daniel Safif, and Mr. Puriya Karimi, my collaborators at UNCC and University of Michigan, and the sponsors of the projects that are happening at my lab. Thank you very much, and I will be happy to answer any questions.
Great, thank you so much for the exciting talk. Any question to Dr. Ghasemi? Okay, I will go with one question until others get ready to ask possible other questions.
Sure.
Very interesting talk, especially on the part that you were trying to come up with a adaptive haptic shared control. However, there's a concern there. The human is competing with another agent, which is kind of now has the role to change. And in the case that it wasn't adaptive, the human already knows what is going to be the action of the controller on the other side. Now it's pretty kind of the human has to learn on the spot how is going to be the reaction of the controller to adjust. For example, if the human going to go based on what is guessing, it may apply too much force, and then the adaptive control is trying to give the control, and now it might end up with quite huge input to the system, right? So because the human is going to go by what has already learned about the impedance of the controller, and that may create kind of confusion on the human side. Let me to give a various sort of kind of more intuitive intuition. Have you been trying at some point take off your shoe and try to push the pedal, right? It takes you quite a long time to learn, now how to drive without shoes, right? Mm-hmm. And that's pretty a small bias in the control input that you're applying to the pedal. Now, not having shoe is going to be completely changing the environment, and that's only a small bias. It's not that much nonlinear behavior that is adding into the loop. Now, this is going to be quite the different situation that now the agent is behaving quite nonlinear way, and it's quite complex, and that situation, how the human should learn to properly act in the case that the other agent may compete or may willing to give the control, and that sort of situation could quite create some sort of problem.
That is very true. We need to look at this adaptive. Adaptively changing it. What we are looking at it as, I would say, is in one iteration. We need to look at it at more iteration, and how this, if I change my behavior, it will impact the human. Human will change its behavior, and then again, the automation will adapt to it. So you're right. There are multiple equilibrium points that we can achieve towards it, and that's when we need we need to study that. That is very, very true. We haven't studied that, and it is one of the projects that we are thinking about it, that what is the effect of changing ZA on the human, because human now, again, there is going to be a loop between these two. If I change human changed its ZH, automation changes ZA. Now human will respond back to the changes. Does it go to one equilibrium point, or how it impacts, or does it make the system unstable? What are the criteria of making sure that the whole thing going to one equilibrium point? These are open questions. I don't know the answers to them. But yes, that is a very important question that we are also thinking, that how we should design that changes such that we make sure that overall the system be stable. We think that we need to change it rather than just keeping it as a constant. But what is the optimal modulation policy can be, that's what we don't know yet.
Thank you.
Yeah, no, but you're right. And then positive conditions, when the vision system says there is an obstacle, but actually not. That is a good question too. We haven't studied that, but what I imagine is, yeah, we haven't studied it. So I imagine that if human is confident in its information, then a human can just hold the steering wheel. And that's one good thing about this haptic shared control is that human can hold the steering wheel very tightly, and automation cannot override humans. But you are right. Looking at the positive condition is important. That I'm not sure if anyone has studied it yet, or maybe they have. I haven't seen anyone have studied this case. But we should study that positive condition and see like how people react to it. That's a very good question. Thank you.
Great. Any other question?
Hello, Dr. Amirhossein. Good afternoon. That's a great presentation. I have one question.
Sure.
My question is in high level that how the control will shift from human to robot or robot to human. It's because that when we are tracking a trajectory, we need to make a very smooth transitions to follow that trajectory tracking. But in your video that I see that when the human has taken the control from the agent, there is a sudden change, sudden jump in the trajectory. And that is happening because I can see your car is moving very fast, and it is some non-stable situation reaches there. This is one problem.
I think that happened after the first video where the driver passing back the control to the automation.
That is, well, you are right. That is okay. You are right. In this experiment that we did here, we set the velocity of the vehicle to be constant. Obviously, when you are designing this transition and control between human and automation, we are only focusing on the steering control, and we are decoupling any type of control with it as well. However, in one of the aspects that we need to consider is when there is a transitioning happening at the steering level, we need to consider the adaptation of the velocity such that again, you're right, we have a smooth path and we don't have such a deviation from the tracking. We didn't do it in this study. This study was just fixed on for the velocity of the vehicle, but when you're doing the transition, I am basically one of the research that we are proposing right now, that when this transition is happening between ZA and ZH, there should be adaptation in theta A as well, in the theta A, and how this theta A needs to be. By theta A, this is just a steering level, but again, the velocity and other aspects should be also considered. So we need to couple, and we need to add we need to add this cost here as well when there is this transition is happening here. But for us, we didn't. We only kept the velocity constant, and that's why you saw that behavior. But yes, you are right.
And as a follow-up question, same thing, sort of, you defined at least 3 modes of operations. How that modes of operation are changing between the fully autonomous and then active and then so on. So how you decide on which mode now the car should be?
Okay. How should, okay, so that is the part that I said it is subjected to future studies, but you are right. For our case studies, we set for those case studies, we set them three distinct behavior. One run was active safety, one run for haptic shell control, one run for autopilot. We didn't tell the participant that what shared control paradigms they are working within, but we knew that what is how automation is active. But you are right. In reality, when between active safety and autopilot, it is basically there's a continuation between these two. That can be set by the weights that you are selecting for your cost functions. And it means that, okay, again, if you are selecting your cost, these weights such that WL2 is bigger than WL1, for instance, in this example, this is active safety and this is assistive mode. The ways that I believe one of the approaches that we can take is, again, is data-driven approaches and designing some reinforcement learning approaches where it gets the information about the human-machine interaction, it gets some information about the environment, it gets some information about the individual agents, and then based on all of that information, it will select the correct WL1, WL2, and WL3. That's one approach that I am thinking about it. We haven't studied it. It is a part of that convention-based studying the convention project that we are thinking about it. But you are right. Selecting these Ws and changing them continuously is something that needs to be done to be able to have it.
I think recently worked on a interesting results on how we can have these operating modes and levels of autonomy adjusted automatically. So we can have a discussion later to see how we can find a synergy here. Any other question? We may have one more question maximum. It's already 4:10.
Yes, I have one quick question about when we have considered that human has the control and human wants to shift this control to the agent, but at that time agent is totally take the control and human has become the observer, because human is not taking any role here. In that case, is not it a human out of the loop system? Because in your whole trajectory tracking, we can see that sometimes human is taking part, sometimes human is observing, but is not giving any input, and sometimes human is sharing. So sometimes when the human is not taking part, that means human is not in the loop system. Human is an observer. Is not it happen? So that the whole system is not human machine systems.
No, yes and no. So we believe with the haptic shared control, one of the disadvantages of a haptic shared control is that the human hands should be on the steering wheel all the time. And with having the human hands on the steering wheel all the time, the human is always in the loop. If human is not applying a large torque on it, or it is like a very passive, it is still in the loop. It is, but the way that we define it, if the human hand is off the steering wheel, then the human is off the out of the control loop. And we are thinking that having the human holding the steering wheel and making the steering wheel move, and the human have this muscle memory of where the steering is, even if the human's intent is not, or the eyes may not be on the road or not thinking about it. That is beneficial. That is beneficial with regard to not have human hands on the wheel and then jump in and take the control. But we know that it may be, honestly, when you are going to commercialization of it, it may be a little bit more annoying to always keep your hands on the steering wheel if you want to buy an autonomous vehicle. So we know that's a limited factor, but we have seen that if human is in the loop, which haptic shared control ensures it by making sure that human hands is on the steering wheel, then that this transition will happen smoother, and people know or understand their roles better. I don't know if I answered your question. But...
Okay, thank you for your answer.
Actually,
Sure,
I think we have to wrap up this meeting. Is already 4:14. Maybe you can later send an email to Dr. Ghasemi for follow-up questions.
Sounds good.
So, and I also invite others, if Dr. Ghasemi is fine, they can send emails and follow the conversation.
Definitely, I would be happy to discuss more about different parts of this project with anyone who's interested.
Great, thank you for a great
Thank you very much, Dr.
presentation. Yes, thank you.
Thank you so much. Thank you, everybody. Thank you.